Hello, everybody.
All right, so warm welcome. We're doing applications of right triangle trig today. There's a few directions that go along with these examples. So I'm going to go through these. It says read the problem carefully. I think that should be sort of like you know that, but read it carefully, read it more than once. Draw and label the triangle, so you're required to draw a picture. Set up the equation, solve the equation, and write a therefore statement. So we haven't talked about therefore statements, but I'll show you this because it's kind of fun. So in Greek, when they originally did proofs, they would do this symbol. It's 3 dots instead of this triangular fashion, and this means therefore. And a lot of times when they would finish proving something, they would sort of sum it all up by putting a therefore statement. So it's kind of fun. We'll go ahead and do that at the end of each example today. It's just kind of a fun little thing we can add on. And then over here, we're going to write out SOHCAHTOA, which is the mnemonic device we've been using to memorize sine is opposite over hypotenuse, cosine, adjacent hypotenuse, and tangent opposite adjacent.
Tangent.
Yep, and we even have a song. And so anyway, put that on the top of your paper. That way that'll help you as we go through each example. So this is basic right triangle trig problems, but we're going to have a story problem that we're starting with. So we're starting with a boy who is flying a kite, and he lets out 300 feet of string, which makes an angle of 52 degrees with the ground. Assuming that the string is stretched taut, which means it's a straight line, not curved. Find to the nearest foot how high the kite is above the ground. All right, so one of the things we are going to neglect in this problem is they don't tell us how tall the boy is, so we're going to assume that basically the kite is at ground level. So I'm going to draw the ground and say this is where the little boy has his kite tied up. Okay, so the kite is up here, it's flying, and so here's the string up to the kite. Okay, and then if we were to find the height of the kite, the actual height, that would be the height straight down to the ground, which will make our right triangle. All right, so let's go back. We've kind of got the general picture. Let's go back and read it again. A boy who's flying a kite lets out 300 feet of string. So which part of the right triangle are we going to put the 300 feet on?
The hypotenuse.
The hypotenuse, good. So that's going to be the string, is the 300 feet, because it's starting here and it's going to over there. The wind's kind of blowing it. It's not a straight up and down situation. And then it makes an angle of 52 degrees with the ground. So am I going to do this angle up here by the kite or this one down here by the ground? The one down by the ground. 52 degrees goes down here. And then assuming that the string is stretched taut, which just means this is a nice straight line for our hypotenuse, to the nearest foot, how high, you're going to find how high the kite is above the ground. So this is what we're looking for. So what we're looking for is the height. So I'm going to label that with our X, or you could use H for height, whatever letter you want. And then we also need to remember, so I'm going to kind of underline the question, that's what we're looking for. We also need to remember that they want us to find it to the nearest foot, which tells us how to round the final answer. All right, so we're looking at this picture. We're going to use the 52 degrees. So let's label the sides. We already said that the 300 feet is the hypotenuse. Which side is X with regards to 52 degrees? Opposite. So if we're looking at SOHCAHTOA, we need the one with the O and the H, which is so. Okay, so that means we're going to use sine. So sine 52 degrees equals opposite over hypotenuse, so that is X over 300. So we read the problem carefully, we drew and labeled the triangle, we set up the equation, we're down to solving the equation. How do we solve this equation? Multiply by 300. So I'm going to take this side times 300, and I'm going to take this side times 300, which cancels out this, and we can just type it into our calculator. 300 times sine of 52, and I just realized my calculator is not in degree mode, so let me try that again. All right, so my calculator gave me 236.403. It kind of goes on. If we're rounding to the nearest foot, what am I going to write as my answer?
236.
So 236, and we're going to label it with feet. Since these are story problems, we actually have real labels today. Oh, I forgot to show you the therefore thing. So this is sort of an extra thing that we wouldn't necessarily have to do, but I'll show you. So this says, therefore, the kite is 236 feet above the ground.
Do we have to write that?
You don't have to. So this is, I'm going to say that this is sort of an optional step. I didn't make up these examples, and it was just whoever made it up put it on there. But this is what that means. It's a little therefore. It's a little Greek symbol. If you want to go into the Greek mathematical history, they just use that at the end of all their problems to show, okay, therefore, this is what I came up with. So it's just kind of a fun thing. But for our purposes, I'll be happy if you just box this answer, and that's fine. Okay, so let's look at example 2. Find, to the nearest degree, the angle which the sun's rays make with the ground. That's sort of a question that they're giving us, right? So I'm going to squiggle underline that. When a flagpole 40 feet high, so that's important, casts a shadow 30 feet long. Okay, so we're going to draw the flagpole. Okay, if you want to put a flag up there, you totally can. I drew mine backwards, so there we go. There's my flag, okay? And so it's 40 feet high, so I can put 40 feet on the flagpole, and it's casting a shadow on the ground that's 30 feet long. So there's my shadow. And then the sun's rays, if it's making the shadow this way, that means the sun's rays are coming down at this angle, and it goes out to about there. So the sun's rays is always kind of a tricky part of it, but it only makes a shadow if the sun's hitting it at an angle. If the sun were directly above the flagpole, it would not make a shadow at all. So that right there. And it wants us to find, to the nearest degree, the angle which the sun's rays make with the ground. So I have an angle up here by the flagpole, and I have another one down here with the ground, so that's the one I want. So I'm just going to call that theta. That little Greek letter, you can call it x if you want to. I like using theta, using my Greek letters. A lot of times they'll use x for the sides and they use theta for the angles, just so you'll know one is angles and one's sides. All right, so this is the angle we're trying to find. We do not have the hypotenuse, nor do we need the hypotenuse. So which side of the triangle would be the flagpole?
Opposite.
Opposite, because it's across from theta. And then what's 30? Adjacent, because it's next to the 30, but it's not the hypotenuse. All right, so which trig ratio uses opposite and adjacent?
Tangent.
Opposite, adjacent, tangent. Opposite, adjacent. Okay, so we've got the song going on. Sokotoa, Sokotoa, Sokotoa. All right, so we have tangent of the angle, that's what we're looking for, is opposite over adjacent. So 40 over 30. Who remembers what we use on the calculator? Go ahead.
It'll be tan -1.
Okay, so to find theta, to get rid of the tangent, we do the inverse. This is called inverse tangent. Inverse tangent of 40 over 30 on our calculators. And if you type that in, it's going to tell you theta is about 53.1, blah, blah, blah. Go back to see where they want us to round it to. They want us to round it to the nearest degree. So 53 degrees is our final answer. And if you want to do a therefore statement, you totally could. But this would be the angle down here. And if you for some reason needed the other angle, it'd be pretty easy because you could subtract it all from 180. All of that works together. Okay, so let's go down to example 3. An airplane rises at an angle of 14 degrees with the ground. Let's just stop there and draw that. So we have the ground. The airplane is here. It's taking off at an angle because they don't fly straight up like helicopters. So it's going this way. And then it's 14 degrees with the ground down here. Okay? And so we could complete this little triangle by drawing a line straight down, putting a little angle. Okay? Find, to the nearest 10 feet, so we're rounding it off to tens, the distance it has flown when it has covered a horizontal distance of 1,500 feet. Okay, so we have the airplane rising with an angle of 14 degrees to the ground. We got that. We want to know, we're looking for the distance it has flown. Well, it's flying on this angle right here, so we're looking for the hypotenuse. And then they tell us it has covered a horizontal distance of 1,500 feet. So horizontal is the straight across, so this is going to go down here. So the plane's actually gone a little bit further than the ground it's actually covered because it's flying at an angle. Does that make sense?
Yeah.
So if we keep in mind, it's probably, this is a really shallow, I probably drew it more like 40 degrees. 14 degrees is not a whole lot. So our answer should just be a little bit more than what this horizontal distance is. And it's good to estimate that in our heads. Okay, we know this is going to be longer than this, but probably not a lot longer. All right, so let's label our sides. What is x? Hypotenuse. If we're using 14, what's this side? Adjacent. So which one uses adjacent and hypotenuse? Cosine. So we're going to have cosine of 14 degrees equals adjacent over hypotenuse. So I have to be careful. I got to put the 1,500 on top and the x on the bottom because it is adjacent over hypotenuse. To the ka in SOHCAHTOA, you have to do C-A-H. The cosine adjacent hypotenuse. All right, so after doing a whole bunch of these the first day, we multiplied by x and then divided by cosine, we decided that there was a shortcut. What is that shortcut? We can just switch these two numbers. And it works every time because that's what happens with our math. So we discovered that shortcut. Yay, us.
Yay.
And so this will just rearrange this, and it becomes 1,500 divided by cosine 14 degrees. And when you type that in, you're going to get 1545.9, yada, yada, yada. Now it says we're going to round to the nearest 10 feet. So instead of tenths, which is where we round a lot, we're going to go to the tens place. So if I have a 4 here and I have a 5 next door, what's going to happen to the 4? It's going to turn into a 5. So I'm going to have 1550, and then we're going to call that feet. Okay. So it's covered 1,500 feet horizontally. It's actually flown 1,550 feet. 50 feet in terms of an airplane is not very far, but it has covered just a little bit more ground than what you actually have on the ground. Covered more space than what's on the ground. I know I'm trying to say it's not coming out. All right, we're half done. Let's go to the next page. All right, it says the top of a 40-foot ladder, which is leaning against a wall, reaches the wall at a point 36 feet from the ground. Find to the nearest degree the angle which the ladder makes with the wall. So I'm going to draw a nice building. There's my nice building. Here's the ground. Okay, and our ladder is leaning against the ground. So this is my ladder. If you want to actually make it look like a ladder, you could get creative here. It's definitely a great picture I just drew. I'm going to fix it just a little bit. All right, so the ladder, the top of a 40-foot ladder. So I'm going to make sure and put 40 on the ladder, is leaning against a wall. It reaches the wall at a point 36 feet from the ground. So where do I put the 36 feet?
Where it reaches it?
Where it reaches. So is that on the building or on the ground?
Oh, is it this one?
So it's leaning against a wall and it reaches the wall at a point 36 feet from the ground.
So it'll be the length of the wall.
So on the building over here, this distance over here is 36 feet. So it's 40-foot ladder, and it's reaching a point above the ground that's 36 feet. Sometimes people see the word ground and they write it on the ground. That's not what it says, so we need to read very carefully. All right, and then we're finding to the nearest degree the angle which the ladder makes with the wall.
So that's right here.
So that would be up here, the angle with the wall, not the angle with the ground. So I'm going to put my theta up here, and here's my right angle. Let's get the whole picture complete. All right, so what sides do we have to work with?
All of them.
Well, we don't have this one.
Then that one.
What's the ladder?
A hypotenuse.
Hypotenuse, it is 40, it's hypotenuse. And then the 36 is next to the angle we're looking for, so that would be the adjacent side. So adjacent and hypotenuse is cosine. So cosine of theta equals, we'll do adjacent over hypotenuse, so 36 over 40.
But cos -1.
All right, so we call that inverse cosine. So we're going to do inverse cosine of 36 over 40. That's the opposite of cosine, or it's the inverse, I should say, not exactly opposite. And so if you put that in, it comes out about 25.8. Remember, they want us to round to the nearest degree. They even italicized it for us. So we have to round off to the nearest degree, which should be 26 degrees. Okay? So when you guys are doing your assignment, you're going to draw the picture. That's a requirement. You have to write down the equation, show me how you're solving it, and then round the answer the appropriate way. So all of this needs to be on the paper.
Do we have to write the original answer and then show us rounding it, or can we just write the rounded answer?
You can just write the rounded answer if you want to. So if you don't want to write down 25.8, you could go ahead and put 26 there. I'm good with that. It's a good question. All right, so let's look at example 5. In an isosceles triangle ABC, AC and CB are each 15 inches. Let's wrap our brains around this. First of all, we know it's an isosceles triangle ABC. We know AC and CB are each 15 inches. So isosceles means two sides are the same. So I notice I have C on both of these. I'm going to put C at the top because then I can make, and put A down here and B over here, because then I can make AC 15 inches and CB 15 inches. And I tried to draw it somewhat isosceles looking. Okay, so this looks a little weird. Angle A and angle B are both 55 degrees. So let's label that. 55 degrees here, 55 degrees there. It's also important information. It wants us to find the length of AB to the nearest inch. So I'm trying to find this down here. Now we're not going to find it directly. We're using right triangle trig, and this is not a right triangle, but
Do we have to split them though?
we're going to split it. Yes, that's a very good guess. We're going to split it and make this into two right triangles. And so I'm going to put an X here and an X here, and then we'll have to figure out AB at the end. So we're actually looking for this whole distance. So we're going to find half of it. So just think of this, now that we've split it up, just cover up half of it. All right?
And what do you do?
And then we'll just do what we've been doing. So 15 would be the hypotenuse, right? Is 55 opposite or adjacent? I'm sorry, the X down here, is it opposite or adjacent, the 55? Adjacent, okay? So if I have adjacent and hypotenuse, that's cosine, we just did that. So cosine of 55 degrees equals, and then we're going to look for this X, so that's your adjacent side, and then that goes over the hypotenuse, which was 15. So we set up the equation. How do we solve it? Multiply by 15. So I'm going to take this side times 15. I'm going to take this side times 15 because that cancels this out. And when you type that in, you get about 8.6. I'm not going to round that off yet, more than that, because I need to think about this situation. So this is 8.6, and this is 8.6. So that means AB is going to be whatever 8.6 times 2 is, or 8.6 plus 8.6, however you want to do that. So 8.6 times 2 is about 17.2. And then how do they want us to round the final answer to the nearest inch? So we're going to say 17 inches, which is good because I could have rounded this number different ways, but no matter how I round it, it's going to come out to be 17 inches no matter what. So good deal. All right, scooting that up. We've got one more, but it has two parts. In rectangle ABCD, it's getting all geometry-y on us. That's okay. Diagonal AC, which is 20 inches in length, makes an angle of 35 degrees with the base AB. Okay, so when it says ABCD, when you draw your rectangle, one important fact about the way that we name polygons is you have to go around the outside. So if I start here with A, I'm going to go B here, and then the next one is C, and this is D. And they make that extra clear by letting us know that diagonal AC is on there. So if you cannot draw diagonal AC, you have to relabel this. So A, B, C, D, I just went clockwise. We drew in the diagonal. And it tells us the diagonal is 20 inches. So we just got all of that good information from right there. And it makes an angle of 35 degrees with the base AB. So they're still talking about the diagonal AC makes an angle of 35 degrees with the base AB. Okay, so base AB, I drew it on the side, but that's okay. I know it's the angle between this and this, so I'm going to put my angle right there. And because this is a rectangle, I know that this is a right angle. So is this one. So theoretically, I should have drawn AB on the bottom, but I still figured it out. It's okay.
Instead of a theta, wouldn't it be 35?
Oh yes, it should be 35. I wrote a theta, thank you. So they do give us 35 degrees. And then on part A, it says we're going to find AB, the base of the rectangle, which I put on the side, but it's okay, to the nearest tenth of an inch. So we're going to find AB to the nearest tenth of an inch. So that's where I'm going to put my X to start with, is right there. Or you could call it AB all the way through if you wanted to. So since we split this rectangle in half across here diagonally, this now becomes the hypotenuse. And what is X? Opposite or adjacent to the 35? Adjacent. And so adjacent hypotenuse is again cosine. It's not always cosine, but that's just how this worked out. So we have cosine of 35 degrees is X over 20. The adjacent side over the hypotenuse. And then we solve by, good, multiplying by 20. You guys got it? So I'm showing you I multiplied both sides by 20. And when we type that in, we get about 16.38. It tells us to round to the nearest tenth of an inch. So that would be 16.4 inches for part A. Okay. Then on part B, it says find CB, the altitude of the rectangle to the nearest tenth of an inch. So we drew it a little funny, but we're just looking for BC. So let me just draw that part of the rectangle. So this is A, this is B, this is C. They gave us, this was 20. We just found that this is 16.4, and now they want us to find BC over here. Do I have to use trig to do that?
Absolutely not.
No. What could we use instead?
180
Normal
minus
math.
20 plus whatever.
Well, they're not angles, though. They're sides.
Oh, okay. Never mind. Don't forget this one.
Remember what this is called?
Yep.
Pythagorean theorem. So we don't have to use trig. We could just put those sides in. Remember that the 20 has to go for C because it's the hypotenuse. So I'm just going to call it x squared plus 16.4 squared equals 20 squared. Thank you. My brain took a vacation there momentarily. So 16.4 squared is 268.96. 20 squared is 400. Where do I go from there?
Subtract 2 minus.
Okay, good. Subtract this from here. You're right. Subtracting that from the 400. And then I get x squared equals 131.04. Am I done?
No, you have to square root.
Ah, we have to square root it. So square root, and we'll come out with x being about 11.447, yada, yada, yada. They want us to round to the nearest tenth of an inch. So if I'm looking at the 10th place, that's 4, and the next place is a 4, so it'll stay 11.4 inches. And that is it.